Yes, good evening everyone. And today we will be starting with third topic structural analysis. We already completed two topics from structural engineering, and today we will be going to complete the third topic, that is structural analysis. Okay, and here you today we will be going on six topics. Okay, principle of superposition, work and energy method, deflection of determinate structures, indeterminate structures, influence line and moving loads, stiffness matrix method, determinate arch and cable. Okay, in that we will be covering these many topics in this today topic. Okay, now first topic is principle of superposition. Okay, and we will be going 4 MCQ on this topic. The principle of superposition is applicable to structures that are linear, elastic, and undergo small deformation. Okay, option A is the correct answer. According to the principle of superposition, the total effect due to several loads acting simultaneously is the sum of effect due to each load acting separately. The option B is the correct answer. The principle of superposition breaks down when geometry changes significantly under load P minus delta effect, or the material becomes nonlinear. Option B is the right answer. In a linear elastic structure obeying superposition, doubling the applied load causes the deflection at a point to double. Option B is the correct answer. Next comes up with the problem. A cantilever beam of length 3 meter and flexural rigidity EI is equal to 40,000 kilonewton meter square carries a 10 kilonewton point load at the free end, a 5 kilonewton point load at 1.5 meter from the fixed end. Determine the deflection at the free end using the principal superposition. Okay, see here there is a cantilever beam and EI is given by 40,000 kilonewton meter square and carries 10 kilonewton point load at free end and 5 kilonewton point load at the distance of 1.5 meter. Okay, total 3 meter length, in that 1.5 meter it is 5 kilonewton load is acting. Okay, they are asking to find deflection at the free end using principle of superposition. Okay, first split the deflection into two separate standard cases and superpose the tip deflection since the beam is linear elastic. Case 1, take P1 is equal to 10 kilonewton, it is acting at the free end and total length is 3 meter. Okay, now deflection is given by P1 L cube by 3 EI. Okay, 10 into 3 raised to cube. Okay, P is 10, L is 3 divided by 3 into EI is given 40 kilonewton. Okay, so that is as 40,000. Okay, when you solve it, 270 divided by 1,20,000, you will get 2.25 mm. It is for case 1. Next, case 2, you will have to take 1.5 meter distance and 5 kilometers a point load acting. Okay, it is case 2. Now, from the fixed end tip deflection formula, now deflection 2 is equal to P2 into A square divided by, sorry, P2 into A square into 3L minus A divided by 6EI. Okay, now substitute the value 5 into 1.5 square into 9 minus 1.5. Okay, 3 into length is 3, overall length is 3. 3 into 3 is 9 minus A is the mid distance 1.5. Okay, 9 minus 1.5 divided by 6 into 40,000. When you solve this, you will get 0.352. Now add both deflection 2.25 plus 0.352, you will get 2.6 mm is the total deflection. Okay, we'll go to the next question is from work and energy method. There are 4 MCQ on this topic. The principle of virtual work state that for a system in equilibrium, the virtual work done by external force equal the virtual work done by the internal force. Option B is the right answer. Castiglione's second theorem is used to find the deflection of point equal to the partial derivative of strain energy with respect to the load at a point. Option B is the correct answer. The unit load method for computing deflection is a direct application, the principle of virtual work. Option B is the right answer. For a stress member carrying axial force P, length L, area A, and modulus of E, the strain energy stored is P square L by 2AE. See, these MCQs are not very simple MCQ. These MCQs are already came in IAS exams as well as previous gate exams. Okay, these are very important MCQ. Please go through these MCQs during the examinations. Okay. Next comes up with the problem. A cantilever beam of length 4 meter and flexural rigidity EI is equal to 60,000 kilonewton meter square carries a point load W is equal to 15 kilonewton at the free end using Castiglianone's second theorem to determine the deflection of the free end. Now, to solve this problem, first measure x from free end. The bending moment at any section is m of x is equal to minus w of x. Okay, hogging and sagging. Okay, sign changes here. Okay, Catalogan's second theorem for deflection under the load is given by deflection is equal to du by dw. Okay, when you differentiate this one, okay, integration 0 to L m by ei into dm by dw into dx. Okay, now since dm by dw is equal to minus x, the integral becomes deflection is equal to 0 to, integration of 0 to L wx by ei into x into dx is equal to w by ei integration 0 to integral of 0 to L x square dx is given by WL cube by 3i. Okay, substitute the value. Deflection is equal to 15 into 4 cube divided by 3 into 60,000. When you solve this one, you will get deflection of 5.33 mm. Okay. Next question from deflection of determinant structures. Okay, the double integration method for beam deflection is derived from differential equation. That is m is equal to ei into d square y by dx square. Option A is the correct right answer. For a simply supported beam of span L carrying a central point load W, the maximum deflection is WL cube by 48 ei. Maclaurin's method is partially convenient for a beam having multiple or discontinuous load along the span. Option B is the right answer. For a pin joint trusses, the deflection at a joint using the unit load method is given by sum of PU PL divided by AE. Okay, option A is the right answer. Next comes up with the problem. A simply supported beam of span 8 meter and flexural rigidity EI is equal to 80,000 kilonewton meter square carries a uniform distributed load of 15 kilonewton per meter over its entire length. Determine the deflection at mid-span. Okay, the deflection for simply supported beam under UDL is given by 5 WL to the power of 4 divided by 384 EI. Okay, W is equal to 15 kilonewton per meter square, L is equal to 8 meter, EI is equal to 80,000 kilonewton meter square. Okay, L to the power of 4 is equal to total length is 8 meter. Sorry, 8 to the power of 4 is given by 4096 meter cube. Substitute all the values in, okay, in the formula 5 into 15 into 4096 divided by 384 into 80,000. When you solve this, you will get the deflection of 0.01 meter. When it convert into mm, it will be 10 mm. Okay. Next, the fourth topic is statical indeterminate structures. Okay, the degree of static indeterminance of a propped cantilever beam is given by 1. Option B is the right answer. In the method of constituent deformations, the redundant reactions are found by equating the deflection at the redundant support to 0. Option A is the right answer. The slope deflection method expresses member end moment in terms of member end rotation and relative rotation of the joint. Option A is the right answer. In the moment distribution method, the distribution factor for a member at a joint is the ratio of the member stiffness to the sum of stiffness of all members meeting at joint. Option A is the right answer. Next comes with the problem. A propped cantilever beam AB of span 6 meter fixed at A and simply supported propped at B carries UDL of 12 kilonewton per meter over its entire span. Determine the reaction at the probe and B. Okay, now the solution, the beam is intermediate to the first degree. Choose the reaction RB at the probe B as redundant and remove it to get released as a cantilever fixed at A. Compute download deflection at B of the released cantilever due to UDL. Okay, that deflection beta is given by WL to the power of 4 divided by AT. Compute the upward deflection B due to the redundant reaction RB acting along the tip. Now, deflection beta is given by RBLQ by 3EI. Apply the computability condition. WL to the power of 4 divided by 8EI is equal to RBLQ by 3EI. Solve for RB, then you will get RB is equal to 3WL by 8. Just substitute the value 3 into 12 into 6 divided by 8, then you will get 216 by 8. That is, when you solve this, you will get 27 kilonewton. Okay, this is the right answer. Next comes up with the fifth topic, influence line and moving load. An influence line for a function at a section shows the variation of the function as unit load moves across the span. Option A is the right answer. For simply supported beam, the influence line of the reaction at support A is straight line value 1 at A decreasing linearly to 0 at B. Option A is the right answer. The absolute maximum bending moment at a section due to series of moving point load generally occurs when the resultant of the load system and the critical nearest load are equidistant from the section. Okay, option A is the right answer. The influence line for a shear force at a section of a simply supported beam shows a sudden jump discontinuity of magnitude 1 at the section. Option A is the right answer. Next comes with the problem on influence line. For a simply supported beam AB of span 10 meter, draw the influence line for the reaction RB and use it to find RB when a single 50 kilonewton point load is positioned 4 meter from A. Also determine the maximum possible value of RB as a load crosses the span. Now the influence line of RB is a straight line, coordinate 0 at A, ordinate 1 at B. You can take 0 at A and you can take 1 at B, varying linearly with the distance, okay, from A as x by L. Yet take x is equal to 4 meter from A, L is equal to 10 meter. The IL coordinate is x by L is equal to 4 by 10. Okay, when you solve this 4 by 10, you will get 0.4. Reaction due to 50 kilonewton load at position RB is given by load into IL ordinate. Okay, you already calculated IL, so 50 into 0.4 is equal to 20 kilonewton. Now the maximum ordinate of the influence line RB is 1, occurring when the load stands directly over at support B. So maximum possible reaction RB maximum is equal to 50 into 1 is 50 kilonewton. Okay, here RB is 20 kilonewton when L is 4 meter and RB maximum is 50 kilonewton when RB is 1. Okay, on X is 1. Okay, next comes up with stiffness matrix method. Okay, here there are 4 MCQ in that first question. In the stiffness method of structural analysis, the primary unknowns are joint displacement and rotation. Option A is the right answer. The stiffness matrix of a prismatic member relates member end process to a member end displacement. Option A is the right answer. For an axial truss member of length L, area A and modulus E, the axial stiffness K is equal to AE by L. Relate axial force to axial deformation. Option A is the right answer. The size of the global stiffness matrix of a structure equal to the number of degree of freedom DOF of the structure. Option B is the right answer. Here comes up with a problem. A steel rod use an axial member 2 meter long as cross section area 500 mm cube and E is equal to 200 GPa. Determine its axial stiffness and the force required to produce an axial elongation of 1.5 meter. See here, the stiffness matrix of a prismatic member is given by K is equal to AE by L. Okay, convert unit. A is equal to 500 mm cube. You can write this 500 mm cube is equal to 500 into 10 to the power of 6 meter square. Next, E is equal to 200 GPa. You can write it as 200 into 10 to the power of 9 Newton per mm square. So Newton per meter square. And L is equal to 2 meter. Compute AE. Okay, just multiply A into E. You will get 500 into 10 to the power of minus 6 into 200 into 10 to the power of 9. You will get 1 into 10 to the power of 8 Newton. And compute stiffness is given by AE by L. 1 into 10 to the power of 8 divided by 2, you will get 5 into 10 to the power of 7 Newton per meter. We can write it as kilonewton meter, that when we will get 50,000 kilonewton per meter. Force of elongation is given by 1.5 mm. Okay, that you can write it as 0.0015 m. Okay, you just multiply 1000, then you will get 0.0015 m. And F is given by K into deflection is given by 5000 into 0.0015, you will get 75 kilonewton. Okay. Next comes up with determinate arch and cable. A 3-hinged arch is statically determinate. Option A is the right answer. For a 3-hinged parabolic arch of span L and central rise H carrying a UDL W over the entire span, the horizontal thrust H is WL square by 8H. Option A is the right answer. For a cable carrying UDL W per unit horizontal length over a span L with sag H, the horizontal tension is given by WL square by 8H. Option A is the right answer. Bending moment at any section of a 3-hinged arch equal the corresponding simple supported beam moment minus H into Y. Y is equal to arch rise at the section. Option A is the right answer. Okay, here one more problem. A 3-hinged parabolic arch of span 20 meter and central rise is 4 meter carries a UDL of 10 kilonewton per meter over its entire span. Determine the horizontal thrust at the support and the bending moment at the quarter span. Okay, now when you go to the solution, horizontal thrust of 3-hinged parabolic arch under full span is given by UDL H is equal to WL square by 8H. Substitute the value 10 into 20 square divided by 8 into 4, you will get 125 kilonewton. And simply supported beam moment at the quarter span X is equal to 5 meter. Reaction is given by WL by 2. Substitute the value, you will get 100 kilonewton each. Now you have to calculate moment is equal to 100 into 5 minus 10 into 5 to the power of 2 divided by 2. When you substitute and get the value 500 minus 125, you will get moment 375 kilonewton meter. Now calculate height of the parabolic arch at X is equal to 5 meter. Formula is given by Y is equal to 4HX into L minus X by L square. 4 into H is 4, X is 5 into 15 divided by 4 meter. You have to write 4000. Here they are given 400. It is not 400. It is 4000. When you solve this, you will get 3 meter. Okay. Next, sorry, it is under 4 meter. Okay. Next, for you have to calculate bending moment in arch at a section. M is equal to M beam minus HY. 375 minus 125 into 3. When you solve this, you will get 375 minus 375. It is 0. Okay. Here the moment is 0 and the height is, and the arch exactly follows the function thrust line shape for the loading. So bending moment vanishes at every section. Okay. Is it clear? Okay. Here we have today there is a solve up to 7 topic. Okay. For a quick revision checklist, you have already gone through the principle of superpositions, deflection of determined structure. Here it comes up with the formula 5WL to the power of 4 divided by 384 EI and WL cube by 48 EI for central point load. Okay, for simply supported beams. And influence line is given by IL ordinate into ordinate into load. Okay, reaction or shear or movement directly for a single moving load. For work and energy is given by delta is given by differentiation of u by differentiation of p. Okay, and intermediate structures is prop cantilever plus UDL. Okay, 3 WL by 8 m, and for a movement is given by WL square by 8. And stiffness matrix method, member stiffness K is given by A by L. And arch and cable and height can be calculated by using formula WL square by 8h. Okay, and these are the topics today you have gone through, and by the next class we will finish up the structural engineering syllabus. Okay, and we'll go more, later we can go for a geotechnical engineering. Okay, thank you. If there is any mistakes in the slide, please forgive us, and we'll be clearing the solve, and we'll be clearing in the later classes. Okay, thank you.